Now that we have defined all the ingredients to do our search, let's see the algorithm that's called tree search that allows us one way to search our search space. So first of all, this algorithm is a function. That this function accepts as input the initial state. This is where we are typically at the beginning. So it's Bain, for example, in San Francisco. And then we also have to provide to this function the goal test. What do we want to be after if we are successful in finding a solution to the problem? Okay, so this function will return either success or failure depending on whether we found a solution to the problem or not. So remember that the search space is divided into three regions. The region that has the explored node, the one that has the unexplored node, and there is a waiting area in between that's called frontier or the fringe. This is where patients wait before going to see the doctor, same thing. So we have some nodes, some states that are actually waiting in the frontier that would be actually the next to be seen by the algorithm. So I'm going to initialize this frontier, this waiting room, with what? With the initial state. So put the initial state in the frontier. This is the next thing that you're going to explore. So how do you explore it? First of all, you're going to check whether this state is actually a goal state or not. So first of all, we're going to repeat this process actually while there are patients in the frontier or in the fringe. We are going to repeat the process several times. So the process is doing what? First of all, you're going to pick a state from the frontier. So you have a frontier with nodes that are waiting to be explored. You pick one of them. The way you pick one of them depends on the data structure that you are implementing. We'll see different ways to do it. So we're going to pick one of them and test if this one is the goal test. So I'm going to pick my initial state, which is, let's say, San Francisco. Is it my goal test? If I want to go to Denver, is it Denver? No, it's not. So what I'm going to do, I'm going to actually, if it's Denver, then I'm going to return success. If it's not, I will need to explore further, in which case I'm going to just include all the neighbors of this state into the fringe. We may put them into the waiting room to be explored next. So I'm going to pick all the neighbors in the state.neighbors, take all the neighbors, and add them to the frontier. So I'm going to put more people in the waiting room to be explored next. So, and the process will continue, will iterate. So I'm going to, again, pick one element from the frontier, test it. If it's the success, then I stop. I return success. If not, I'm going to continue exploring my search space and growing my tree accordingly. So this is how the tree search is being done. Let's illustrate this tree search algorithm on our map example, in which we want to see what would be the path to go or the way to go from San Francisco to another city, let's say to Chicago. So our initial state is Bain in San Francisco, and the goal state is to be actually in Chicago. All right, so let's show the first steps in growing a search tree to find a route between San Francisco and another city. In this case, we are going to maybe focus on Chicago. So here's the algorithm on the right side, and here's the map. And this is representing actually our search space represented by a tree. Okay, so we have this exploration tree in which we are going to try to find our way from San Francisco to another city, let's say Chicago. All right, so initially, we are going to initialize the frontier with the initial state. The initial state is Bain in San Francisco. And this is actually going to be our root node that actually is showing up here in gray because it's in the waiting room, or otherwise it's in the frontier, right? So we are putting this node here, the state of Bain in San Francisco in the frontier. This is what we need to explore next. So observe here that San Francisco has 3 children. This is the possible cities we could go to from San Francisco. So if we drive, this is the action. If we drive to Los Angeles, then we will be in Los Angeles. Otherwise, we could drive to Portland or Salt Lake City. And if you see the map, these are the possibility to go from starting from San Francisco. Okay, so all these nodes here are actually all white because they are unexplored nodes. Okay, so the white are unexplored. And this one is on the fringe. Okay, the next step is then to see the children. So we are going to test why the frontier is not empty. Yes, it's not empty. It has San Francisco. The state is frontier.remove. So I'm going to pop this from the frontier or from the waiting list and check it. If it's the goal test, is it Chicago? No, it's not. Then we're going to not send a success yet. We're not successful yet. We're going to check the neighbors of San Francisco, and the neighbors are this guy here, Portland, and Salt Lake City. And we're going to add these neighbors into the fringe, which will bring us to the configuration in which we have actually this node being explored in orange. And these 3 nodes now are in the fringe. These 3 are in the fringe, right? Because they are going to be explored next. And these remain unexplored. So observe that from Los Angeles, we can go to El Paso, to Phoenix or Las Vegas, or even San Francisco back. So these are the 3 nodes. So what we're going to do is we're going to reiterate in our loop here and remove one element from the frontier. So I'm going to remove Los Angeles. Is it the goal test? Is it Chicago? No, it's not. Then I will keep going. I will add all the neighbors of the state of Los Angeles node into the fringe. So I'm going to add El Paso, Las Vegas, Phoenix, and San Francisco. So this will bring me to another new configuration in which we have the node Los Angeles is explored, San Francisco is explored, and now I'm adding to the fringe El Paso, Las Vegas, Phoenix, and San Francisco. So I'm going to put all these gray nodes in so these are already in the fringe, but I'm adding these 3 to continue my exploration. All right, so and the process goes on until we actually are either successful in finding the goal test of Chicago, right? Or we are not successful and we simply return failure if we never return success before. Observe here that actually what happens with the Los Angeles, that San Francisco is a child of Los Angeles, which means that we can keep going and bounce back between Los Angeles and San Francisco within the tree, which means that we're going to end up with actually an infinite search space, which is a problem, and our traveler will never actually go from San Francisco to Chicago. So in order to fix that, we're going to put some more constraints on this algorithm by making sure that we are not going to revisit nodes that have already been visited. So this configuration here from going from Los Angeles and San Francisco should not happen. We're going to make sure that this doesn't happen by modifying the algorithm. To handle repeated states, what we're going to do is to transform our algorithm from a tree search into a graph search algorithm. So the only change here that's happening is the change in the algorithm, which actually has also an initial state and the goal test as the input. Always returns success and failure. However, the main changes that we could observe on this algorithm is actually adding a new set called explored, that actually we set to new, initially an empty set. But then whenever we remove an element from the frontier, we're going to add it into the set of explored states. And also, whenever we check that, when we pick the neighbors from the state.neighbors, we're going to check whether they have been explored before, whether they are already in the frontier or explored. So by doing so, in our previous example, once we have explored San Francisco and we go to Los Angeles, the kids or neighbors of Los Angeles are, one of them is San Francisco, but because San Francisco has already been in the frontier or the explored set, we're going to avoid doing that and only explore the nodes that are actually have not been explored before. So this will avoid us to have infinite loop in bouncing between Los Angeles and San Francisco in our search. So now that we know how to search and define a tree search and how to be careful on not making loops, we are going to need to define also what we call a search strategy, which is actually defining a way to pick the order of node expansion. So we know that there is a fringe, and there are nodes that are waiting on the waiting list to be explored. The way we pick those nodes is called an order of node expansion, and we need to be able to do that. So there are different ways to evaluate, different dimensions to evaluate our strategy. The first one is called completeness, which means that do we always find the solution if it exists? So we need to adopt a strategy that actually leads us to success. We also evaluate the strategy with respect to time complexity, which is actually approximated by the number of nodes generated and expanded. So this actually gives us how much time we spend in finding our goal when we search. The fourth dimension is called space complexity, which is how much memory do we need. It can be approximated by the maximum number of nodes in memory at the same time. So this will be the maximum that we need to use in order to solve the problem. And finally, the optimality, do we always find the least cost solution? So if you go from San Francisco to Chicago, we don't want to go all over the place and go through New York and go back to Chicago. So for example, this is a way to evaluate the cost, which would be the number of kilometers spent on the road. And this could be, we could also aim to not only find, be complete and find a solution, we also aim to find the least cost solution, which will make our search optimal. So specifically, we're going to measure the time and space complexity in terms of what? In terms of B, which is called the maximum branching factor of the search space. This is actually the actions per state. So suppose we have a node, and this node, from this node we could perform any of these actions to lead to this nodes. So this number here is called B, which is the branching factor, which is the maximum possible from one node to the other nodes. And we are going to call D the depth of the solution. So suppose we have been exploring the tree, and we did find a solution here. So the depth here is called the depth of the solution. And finally, M is the maximum depth of the state space, which could be potentially infinite. In the following lectures, we're going to talk about two kinds of search. We're going to distinguish between an informed search and informed search. An informed search is when we have no information about the domain. An informed search, we have some information about the goal and the domain in general.